The protocol uses proprietary message protocols, and this is pretty common with a lot of commercial software. Some of them you'll see combinations of leveraging well-known standard protocols or techniques along with their own customized message protocols. We tend to find that, well, in the case of Plugboy, we'll see that it starts to look fairly standard until you get to the real juice of the protocol. So we'll be talking more about this format, but just bear in mind that it's sent with a binary format that is consists of a header, then data segment. Data segment is compressed, and that is base 64 encoded. One could say that this was being done just for transportation purposes, but sometimes the products may be using this as a form of obfuscation. So bear that in mind that there's a conception amongst a lot of commercial software that if you obfuscate your protocol so that it doesn't look recognizable, it will be safe from attack for at least some period of time.
The fact that the reporting channel is not authenticated, I don't know, it might not sound surprising just because you assume that the vendors are negligent about things like that. But it's a hard problem to actually handle authentication in this environment. As soon as you install something on 1,000 different machines, what are you going to do? Have 1,000 different public key pairs between those two machines to actually authenticate the channels? No, you're not. You're going to come up with something much simpler than that, if anything at all. The goal of these systems is to get reports from these end systems when things are detected as quickly as possible. That's the goal that they try to solve. Anything they do to authenticate the system might actually hurt the amount of alerts that they get into the system. So don't be surprised to find out that the authentication on the system, especially the verification that the client that is talking to the agent is who he says he is, don't be surprised to find out that that stuff is exceedingly weak. Sometimes the authentication from the server to the endpoint agent is relatively strong because the server to agent channel, everyone knows, allows people to update the binary and does all sorts of sensitive security stuff to it. But when the agent reports things back to the server, we're usually not surprised to find out the authentication mechanisms there are weak. For instance, they might use machine credentials instead of normal credentials, or domain credentials, so that anybody who has a login on any machine on the entire network can make a connection to the reporting server. And we're going to talk in a second about what that actually means. We also want to talk a little bit about how you would look at a binary protocol like this and figure out what it was doing.
Okay. So yeah, just to reiterate too, there are reasons for why we didn't incorporate authentication into the Plugboy protocol, and Tom just touched on them, is that what are you going to key authentication off of? One thing to bear in mind about extrusion detection products is that they don't want to prevent another blockade for the alerts from working. So if you are, for some reason, the authentication fails, it means that something isn't going to be alerted and it's going to miss stuff. So that becomes yet another evasion attack. Okay, so we're going to talk about protocol reversing, and this is maybe something that can be taken away from this. This is a very useful approach for when you're dealing with proprietary products of any kind, and a lot of the extrusion detection products out there, or the ones you're likely to run across, are going to probably incorporate some kind of proprietary protocol. It may be just in the reporting protocol, it may be elsewhere. So these concepts may apply elsewhere. We're going to be talking about reversing the Plugboy reporting protocol in particular, but the concepts here can be used elsewhere.
By the way, let me ask right now real quickly, just because I want to make sure everyone knows about Pedram. How many of you guys in the audience know about Pyme or about Pedram Amini? Very few. This is excellent, so I get to explain this and take credit from him or whatever. So one of the tools that we use for these types of engagements to learn how proprietary protocols work is a tool designed by a guy who's giving a talk against us right now. You should be at his talk because he's cooler than we are. A guy named Pedram Amini, who wrote a Python debugging toolkit called Pyme, which is named after the old wizened martial arts master in Kill Bill. What it does is basically it takes an IDAPRO disassembly, which you can get from any binary, from any program instantly. You just pull it into IDAPRO, you get the disassembly out, looks at the disassembly, and breaks it into tiny little chunks of code called basic blocks. Pyme reads the basic blocks into a database and then attaches itself to a running service on a box, say the service or the client, either side of it, right? That attaches itself to a running Windows process. And it installs breakpoints at every single one of those basic blocks. So at tens of thousands of locations inside of the binary now. There's a breakpoint installed that halts the program when it hits that breakpoint. Now, the clever trick that Pedram came up with is that when that breakpoint gets hit, all that happens is that PyMay records the breakpoint got hit, and then it removes the breakpoint so it never hits again. So what you wind up getting is a trace of all the basic blocks that are running in the program. Now, that's cool in and of itself, but what PyMay does and what we use to do protocol reversing is you can get a baseline reading of a program as it's running and see what code is running in the background all the time, kind of the ambient load of the program. And then you can run network packets against it again and see what differs, what changes every time you try a different type of packet. You can brute force a protocol doing that. It's a binary protocol. You have no idea how it works. You randomly change bytes, and you see if the PyMay trace differs each time. That's a feature of PyMay as you do that. And what will happen is that the binary, as it runs through the program, without me doing any binary analysis whatsoever, will betray what the important fields are and what it's doing. And we can use that to find out where the important fields are and what to change and how to play with the protocol. So this is an example of the type of weaponry we have to get through proprietary protocols. So if a vendor ever tells you that proprietary protocol is a stumbling block for us to actually analyze the protocol, ignore that. That's irrelevant, completely irrelevant. Proprietary protocols are fun. We like dealing with them. They're not a real challenge.
Okay, so there's one last piece on there. So not everybody may be familiar with our plug there, which is our own. We use a tool that we developed called BlackBag. It's available for download on our site. That's the only plug I'm going to give to it. But I just want to explain what it does so if it's not completely clear. It's kind of like a netcat on steroids. And there are other programs out there like that claim the same thing. I'm not going to say this is better or worse, but it's definitely a useful tool. I've grown quite fond of it. It's worth checking out. So just if you're not familiar with what BlackBag does, think of that piece as like a netcat or a socat. Okay, so Tom talked about the program analysis sides, and I want to make a point that what I'm going to talk about here are the protocol decoding attacks, or not attacks, but the process of decoding and understanding an unknown protocol. It's really difficult to get a really good picture of how something works just by doing one or the other. And I think in order to be able to do what Tom's talking about, you have to be doing some of this first, but to make it valuable. And we'll talk about some of the things that are valuable inherently about doing this for Plugboy, but for the protocol reversing concept, to make it useful and valuable, combining it with some kind of program analysis like PyMay, as Tom talked about, is going to make it really much more useful. Okay, so when you're looking at an unknown protocol, at some point you're going to be looking at a raw blob of data. I want to make it clear here that, as I said, the Plugboy protocol was base64 encoded. What we're looking at here in this hex dump is not base64 encoding, so it's already been base64 decoded. You can assume it's fairly easy to implement one of those. You usually have a hook in a scripting language. If it's not something that, if you're not a programmer, you don't necessarily have to be, I guess is what I'm trying to say. The tools are pretty easy to find and incorporate.
And in Plugboy, by the way, and where you'll see base64 encoded protocols a lot is you ask your vendor what the protocol is, and they say, well, it's firewall friendly. It runs over HTTP. It's not a scary application at all. And you look at the requests it's doing in there, like in Plugboy, HTTP post requests. And the payload of those post requests is a base64 encoded message. You can tell it's just a jumble of letters and numbers and stuff, right? Bet on it that when you see one of those messages going back and forth between a protocol, what that is, it's a proprietary, scary binary protocol being tunneled over HTTP. It adds no security to the fact that that's actually running over HTTP. It's just as scary to your firewall and to the security of your network as if it was just running natively on the network. So you'll see base64 encoded binary protocols all over the place. We love it when we see these things, right? Because chances are we're the first people outside of the company to ever have looked at that protocol.
Okay, so what we're looking at here is once we've taken that base64 chunk that we've seen Plugboy using and pulled it out, this is what it's going to be looking like. I don't know how easy it is to see, particularly for people in the back, and for that I apologize, but I'm going to describe what this header looks like. And this slide, if you're particularly interested in this fake protocol that we've created, it'll be in the slides available off the website after BlackHat, possibly at the end of the day today. So, but basically these are some common things to look for too. I'm going to talk about that a little bit because you're going to be looking for the common things to find in any kind of protocol, let alone a proprietary one. You tend to see some commonalities between a lot of different approaches. So it's really common that the first line or so of your hex dump, the first X bytes of your message packet are going to be some kind of a header, and this just has to do with the way that things are deserialized by programs. So just bear that in mind. If you're a programmer, I don't need to tell you these things, but if you've never really looked at this sort of stuff, that's a good tip to bear in mind.
You can tell if something's a message type, for instance, because it'll repeat from message to message. You always see the 00000002 every message. Well, that's probably a message type, right? You can tell a sequence number because the increments, because they're sequence numbers, right? You can sometimes pick out version numbers. They're really clear. Data lengths, you can automatically pick out data length fields just by matching every offset to see whether it frames properly. So a lot of these protocol features are pretty straightforward to pick out, and as soon as you pick them out, what you do is you write a fuzzing toolkit. I think one of the things that we want to point out here, though, is that if we look at this data here, it looks all jumbly, right? It looks like there's really not a whole lot of structure in it. There's a formal measure of how jumbly a piece of data is. It's a new term I've invented, it's the jumbliness. But the real term of it is entropy. And there are a variety of tools. If you Google for ent, there's a really good one that you can just pipe data through a shell script, and it'll give you a measure of how random the data is, which we did here in this case, right? And this is highly random data. A good, signifier that data might be encrypted, which we think would be a good thing in this case, right? You probably should encrypt the data for the reports that you're sending back to the server, because what you're reporting on is, pretty sensitive stuff. So we look at it, we say, well, is this encrypted? How will we know? Well, we have a number of other things to test before we decide to give up, because it's, a custom keyed encrypted, protocol.
Okay, right. It's very hard to see in here, and we had colorized these, and I apologize if they're not colorized anymore on the text, but if you can make it out, this is broken into a ping segment, which is the message header. That would be like the first line of this hex dump. And if you can't read it from back there, you'll see at the beginning of that it has pboy as a message name. That may seem really like, that's convenient, but actually you'll see a lot of times some kind of a token message at the beginning of your protocol, and that can actually help you get some more information if you're completely reversing it in the black. Then there are several binary values, one of which, as Tom talked about, is the data length of that segment. And you can tell it's a data length because it happens to match the size of the rest of the packet. So maybe obvious stuff, but sometimes it can be hard when you're looking at this chunk of data to make that out.
And Plugboy, if you see the data length in the protocol, and then you make a packet that's 10,000 bytes long, and you send that, you also take over the Plugboy server. So
right,
just,
exactly.
Just so you know.
And when you're looking at these protocols, things like, bear in mind that that's being read into a buffer. So these are all of these fields, particularly when you see that number there, that length, you determine it's a length. That's something you're going to, if you're fuzzing, you're going to be fuzzing that field for sure.
The way you tell if high entropy data is encrypted or not, or whether it's compressed, is simple brute force. There are only a small number of compression algorithms that people ever actually use. In the real world, it's almost entirely zlib. So we have a tool which you can download from us. It's been around for a while. Jeremy Rausch invented it. It's the greatest tool ever. It's called DZ, and what it does is it sweeps through a binary and it finds compressed segments within the binary. And if you run DZ on the Plugboy protocol, what you find is that there is a zlib compressed segment inside of it, that high entropy data is not encrypted, but is in fact simply compressed. You wouldn't know it to look at it, right? The vendor could tell you that field was encrypted, and you probably wouldn't have a good idea whether it was or it wasn't. But when you actually look at the protocol under the hood, you find out that it's compressed. Another way you can do that is to disassemble the binary and look for calls to the crypto APIs. We didn't find those because it's not in fact encrypted. It's simply compressed.
Right, and similarly, if you see a lot of calls to a zlib, what else would it be doing with it in the aspect that you know is doing the reporting agent, then you know for sure that it probably is at least compressed somewhere along the way. So Tom mentioned that you can use an automated tool to catch compression, but I wanted to point out too, again, it's hard to see, but the way that DZ works is it looks for these signatures that give away compression, basically the compression formats. Here we were able to tell this without actually using DZ that this was a compressed message because of the header and the tail.